Ever pondered about the possibility of life beyond Earth? The idea is truly captivating, isn't it? It's a question that stirs our collective curiosity and ventures into the realm of the unknown. Yet the search for extraterrestrial life is far from straightforward. These potential life-bearing worlds are not only distant but also much dimmer than their host stars. Imagine trying to spot a tiny firefly next to a brilliant floodlight from miles away. That's the challenge we're up against. And it's not just about seeing these planets and moons. It's about deciphering the clues they might be giving us. If life exists on a global scale on these celestial bodies, it could leave signals in their atmospheres. Like unique fingerprints, different types of biological activity could leave specific atmospheric imprints. But the question remains, so how do we look for signs of life in such distant, elusive worlds? Astronomers have devised ingenious methods to detect planets orbiting distant stars. Indeed, the cosmos is an astronomer's playground, and their toolbox is filled with creative techniques and instruments to explore it. One such tool is the method of transit spectroscopy. This method is used to infer an exoplanet's chemical composition. When a planet passes in front of its star, as seen from Earth, the planet's atmosphere absorbs some of the starlight. The resulting absorption spectrum appears something like a jagged mountain range. The valleys in this cosmic landscape correspond to different chemical elements that absorb the starlight. From this, we can infer whether there is any kind of biological activity there. But the universe doesn't just hand us these answers on a cosmic silver platter. We need to know what to look for. And that's where the concept of atmospheric fingerprints comes into play. Just as our fingerprints are unique identifiers, different kinds of biological activity leave specific imprints in a planet's atmosphere. These imprints, these atmospheric fingerprints, can be thought of as cosmic calling cards, signaling the presence of life. Take our own planet, for example. The abundance of oxygen in our atmosphere produced by photosynthesis is a clear signal of life. If we were to detect a similar abundance of oxygen in the atmosphere of a distant exoplanet, it could suggest the presence of photosynthetic life forms. Each exoplanet, like each human fingerprint, is unique. No two are exactly alike, and each has its own story to tell. The art and science of astronomy is about learning to interpret these stories, to read the atmospheric fingerprints left by different kinds of biological activity. Now, the real challenge lies in deciphering these atmospheric messages. Just as a forensic scientist must carefully analyze fingerprints to draw accurate conclusions, astronomers must carefully analyze the atmospheric fingerprints of exoplanets. Their task is to sift through the cosmic noise and find the clear signals, the undeniable evidence of life beyond our own blue planet. The universe is speaking. We just need to learn how to listen. This is where information theory steps into the picture. But what is information theory, you might ask? At its heart, it's a powerful tool we use every day in modern communication. It helps us sift through a cacophony of signals to find the meaningful messages hidden within. Picture it like this. You're in a crowded room, filled with people, all talking at once. Amid the noise, you're trying to listen to one specific conversation. Information theory is the tool that helps you filter out the background chatter, to focus on that one conversation you're interested in. Now imagine we apply this theory to our search for alien life. Instead of a room full of people, we have a universe filled with stars, planets, and moons. Amid this cosmic noise, we're trying to pick out the specific signals that might indicate biological activity. Think of it as listening for the whispers of life amid the symphony of the universe. So, how do we do this? It's a two-step process. First, we capture the light from an exoplanet. Remember, this light may hold hidden messages about the chemical composition of the planet's atmosphere. If life exists there, it might have left its fingerprints in the form of specific atmospheric imprints. Once we have this light, we then use information theory to search for chemicals associated with the presence of life. In our cosmic conversation, these chemicals are the words that form the sentences of our interstellar message. The presence of certain chemicals might signal the existence of life as we know it. Just like in a crowded room, the key is knowing what to listen for. We need to tune out the cosmic noise and focus on the potential whispers of life. With the right tools and a bit of luck, we might just be able to pick out these whispers from the cosmic cacophony. So, we have the tools. But what are the challenges? The promise of detecting alien life is exciting, but it's not without its hurdles. As we probe the cosmos, we're confronted with a cascade of assumptions and questions that challenge our understanding of life itself. In our search for extraterrestrial existence, we've been primarily looking for signs of life as we know it. But what if life out there doesn't play by our rules? What if it's not carbon-based or doesn't require water? These are questions we must grapple with as we expand our search. Let's consider atmospheric biosignatures. These are chemical imprints left in a planet's atmosphere by biological activity. On Earth, for example, oxygen is a prominent biosignature, a product of photosynthesis. But what if alien life forms don't photosynthesize? What if they breathe methane or some other compound we've yet to consider? Discovering an unfamiliar biosignature could be like finding a new letter in an alphabet we thought we knew. It's a thrilling prospect, but also a daunting one. Another pivotal aspect to consider is the evolutionary stage of the planet. Life, as we've seen on Earth, can dramatically alter a planet's atmosphere over time. From the first emergence of life around 3.5 billion years ago to the present day, Earth's atmosphere has undergone radical changes. An alien astronomer observing Earth at different geological epochs would note significant shifts. Therefore, when we observe distant exoplanets, we must remember that we're catching them at a single moment in their evolutionary journey. Finally, we must take into account the characteristics of host stars. They come in various sizes, temperatures, and life cycle stages, all of which influence their planets differently. A hot yellow star might nurture life differently than a cooler red one. We're standing on the brink of a new era of discovery, teetering between what we know and the vast unknown. The challenges are immense, but so are the possibilities. We are just beginning to understand the vastness of the universe and the myriad possibilities it holds. Despite these challenges, the potential of information theory in the search for extraterrestrial life is immense. This powerful tool, which we already use to sift through the noise in our modern communications, can be the key to unlocking the secrets of distant worlds. Imagine using the principles of information theory to decode the atmospheric imprints left by alien life. Similar to how we interpret letters of an alphabet to form a sentence, we can discern specific chemicals in an exoplanet's atmosphere, each one acting like a unique character in an interstellar message. This is not just a theoretical concept, it's a practical application of the same principles used in our everyday digital communications. Now, let's circle back to transit spectroscopy. This method allows us to infer an exoplanet's chemical composition by observing how its atmosphere absorbs starlight. With information theory, we can go a step further and discern possible signs of biological activity. The valleys in the absorption spectrum, corresponding to different chemical elements, become parts of a coded message waiting to be interpreted. Of course, this approach does not come without its challenges. We're assuming that these biosignatures are indicative of life as we know it, based on Earth's example. The truth is, life on other planets could be radically different from what we're familiar with. But with the help of information theory, we can broaden our search parameters, looking for the unexpected and the unfamiliar. We also need to consider the stage of a planet's evolutionary history that we're observing. Life has drastically changed Earth's atmosphere over billions of years, and the same could be true on other worlds. Information theory can help us understand these changes, offering clues about the potential presence and evolution of life. As we continue this incredible journey of exploration, who knows what we may discover in the far corners of the universe? Armed with our telescopes and the power of information theory, we stand ready to decode the cosmic signals that could lead us to the discovery of alien life.